How to study the harmonic oscillator phenomenon in chemistry. This article gives an overview about the harmonic oscillator phenomenon in chemistry for chemistry students. Steps 1. Learn the definition. Harmonic oscillations refer to a physical phenomenon in which an object of mass m is doing a periodic motion under the effect of a restoring force which tends to force the object to its original state of equilibrium. This phenomenon was originally formulated for classical mechanical systems such as the periodic motion of a pendulum. This harmonic motion in classical mechanics is depicted mathematically using the following equation. F equals kx, where F is the force that is acting on the mass m and x is its displacement from its equilibrium state and k is a constant. The minus sign comes here to designate the fact that it is a restoring force to an equilibrium state. 2. Learn about its role in quantum mechanics. The classical mechanical phenomenon of the harmonic oscillator has similar representation in the theory of quantum mechanics. In the theory of quantum mechanics, it finds use in the description of vibrational movement of bonds between atoms. The quantum mechanical description of a harmonic oscillator is much more difficult and complicated than its classical analog. The harmonic oscillator in quantum mechanics is solved using the time-independent Schrödinger equation, which uses a potential in the form of V equals 1, 2 kxx. This potential energy value for a harmonic oscillator is the classical value and is used in the Schrödinger equation to find the corresponding quantum mechanical value. 3. Consider that the solution of the Schrödinger equation for a harmonic oscillator is not straightforward such as its classical analog. The solution of this problem can be done in one of two ways. One is to use the commutation relation of operators in order to find the eigenvalues of the quantum mechanical harmonic oscillator. For this purpose, one uses special form of quantum mechanical operators that are called raising and lowering operators. These are convenient forms of operators that help much in the solution process of the problem. The other method that is used to solve the problem of the harmonic oscillator is to solve a fairly complicated differential equation that involves a potential form that is difficult to handle mathematically. The differential equation for this system is not straightforward to solve, and one must first find an asymptotic solution to the problem for large values of the displacement r. After that, one uses a power series method in order to find a general solution of the problem. The result in both of the suggested methods is that the energy eigenvalues that are obtained are E equals h asterisk, ni, n plus 1, 2. From this equation one gets an interesting result, which is the ground state energy for a harmonic oscillator is not zero. This result is in accordance with principle of uncertainty. 4. Note that this method of treating the bond between two atoms as a harmonic oscillator is a fairly good approximation that gives good theoretical results that are comparable to experimental results. The vibrations of bonds between atoms are used to find the normal modes of a molecule. This is done in order to decide if the molecule will absorb light in the infra-red region of the spectrum or not. It is also used to decide if the molecule will absorb light in the Raman region of the spectrum. The wave functions of a harmonic oscillator have a complicated mathematical form that can be either odd or even. Within the vibrational levels of a diatomic molecule and other molecules, there are rotational energy levels spread between each pair of adjacent vibrational levels. Rotational energy levels of the diatomic molecule have higher wavelengths than that in the vibrational region of the energy levels of a molecule. Rotational spectrum is useful for giving information about bond distance and about rotational transitions in the molecule. 5. Learn about the vibrational energy levels of a molecule. They are located in the infra-red region of the light spectrum. The vibrational level spectrum is important in giving information whether the molecule absorbs light in the infra-red region and show IR spectrum or not. Also, the vibrational spectrum is important in certain types of lasers, such as the CO2 laser, which is a typical laser that is based on transitions between vibrational levels. The vibrational energy levels of a molecule are located between electronic energy levels. Between two typical electronic energy levels there are several vibrational energy levels. The electronic energy levels are spaced more energetically than both the vibrational and the rotational energy levels. The electronic energy levels are more significant than both vibrational and rotational energy levels due to the existence of electronic transitions in these energy levels, which is important for the formation and breaking of chemical bonds. 6. Learn about its uses. The harmonic oscillator on the atomic level finds use in solid-state chemistry in which the atomic vibrations in the solid are treated as harmonic oscillators. Approximating the movement of atoms in a solid material using the harmonic oscillator approximation is a good approximation that can give information about the solid itself. Finally, in certain types of liquids which are called quantum liquids, the atoms of such a material are sometimes treated as harmonic oscillators, such as the molecules of the superfluid helium.